Good morning, class. We are looking at chapter 6, exponential and logarithmic functions. 6.1, exponential functions. 6.2, graphs of exponential functions. So in this chapter, we cover exponential functions, graphs of exponential functions, logarithmic functions, graphs of logarithmic functions, logarithmic properties, exponential and logarithmic equations, exponential and logarithmic models. The objective here, evaluate exponential functions, define the number e, solve exponential equations, find the equation of an exponential function, use compound interest formulas, evaluate exponential functions with base e, graph exponential functions using transformations. Reminding everybody, summary of polynomial functions. Polynomial functions are in the form of f of x equals a sub n x to the power of n all the way to a sub 0, where a sub n can't be 0. N is a whole number, meaning 0, 1, 2 to infinity. The domain is all real numbers from negative to positive infinity. Degree of a polynomial is n. Graph is smooth and continuous. Maximum number of turning points is n minus 1. At a 0 of even multiplicity, the graph of f of x touches the x-axis. That means it cannot cross. At a 0 of odd multiplicity, the graph of f of x crosses the x-axis. Between zeros, the graph of f of x is either above or below the x-axis. And behavior. For large values of absolute values of x, meaning going to negative or positive infinity, the graph of f of x behaves like the graph of its leading term, y equals a sub n, x to the power of n, the leading term. As an example, polynomial of degree 1, p of x equals mx plus b is a linear function. Of degree 2 is p of x equals ax squared plus bx plus c, which is a quadratic function. And as you recall, it has a vertex at x equals minus b over 2a, and if you plug it into f of x, f of minus b over 2a gives you the value of its y coordinate. Zeros of polynomial function. First and foremost, let's define the division algorithm. N of x over d of x is q of x plus r of x over d of x. Or you can say n of x equals q of x times d of x plus r of x. Dividend equals the quotient times the divisor plus the remainder. The remainder theorem says if you're dividing f of x by x minus c, then the r, or the remainder, is simply evaluate the function at c. Factor theorem says we do the same thing, and that r must be 0. Then x minus c becomes a factor of f of x. The intermediate value theorem, or IVT for short, if f of x is a polynomial function or any continuous function, and if for real numbers a and b, the values f of a and f of b are opposite in sign, then there exists at least one real zero between a and b. In short, you have a continuous function. F of a is negative, f of b is negative, f of b is positive, so 0 is in between, and the graph must cross the x-axis, resulting in a root or 0 of a function. Number of zeros theorem. A function defined by a polynomial of degree n has at most n distinct unique complex zeros. The rational zero theorem indicates if f of x is the following polynomial, a sub n, x to the power of n, all the way to a sub 0, then the rational zero indicates that it has to be the factors of a sub 0, the constant, over the factors of a sub n, the leading coefficient. That would be possible rational zeros. Fundamental theorem of algebra indicates if p of x is a polynomial of degree 1 or more, then there is some number k such that p of k equals 0. P of x equals x minus k times q of x, where q of x can also be factored, resulting in p of x equals a times x minus k sub 1 all the way to k sub n, resulting in n roots, n complex roots. Conjugate zeros theorem. If P of X defines a polynomial function having only real coefficients, and if R equals A plus BI is a zero of P of X, then the conjugate R bar equals A minus BI is also a zero of P of X. Odd degree polynomials therefore have at least one real zero, since complex conjugate zeros happen in pairs. Rational functions. A function f is a rational function if f of x is n of x over d of x, where d of x can't be zero. Remember, we can't divide by zero. Where n of x and d of x are polynomials. That's the restriction. The top and the bottom must be polynomials. The domain of f consists of all real numbers except the zeros of the denominator of f of x, which is d of x. In other words, you set d of x equal to 0 and you exclude that becomes the domain. Rational function in lowest term, f of x equals n of x over d of x. If we know this is in lowest term, then VA or vertical asymptote can be found by setting the denominator d of x equal to 0. But it is important to be in lowest term. If there is a common factor, you must drop. Finding the horizontal and oblique asymptote of a rational function, which is in the form of n of x over d of x. The numerator is a sub n x to the power of n all the way to a sub 0, and the bottom is b sub m x to the power of m all the way to b sub 0. That means the degree of the numerator is n, the degree of the denominator is m. If n is less than m, horizontal asymptote has the equation y equals 0. If n is equal to m, they have equal degrees, then the leading terms take over, and y becomes a sub n over b sub m, the ratio of the leading coefficients. Finally, if n is precisely 1 more than m, that means m plus 1, then we do the division, long division or synthetic division. It results in mx plus b, which is a linear function, plus some remainder over d of x. This linear function y equals mx plus b is the oblique asymptote, also known as slant asymptote. Inverses and radical functions. Function has the following definition. For each x in the domain of f, there is exactly one image f of x in the range. However, an element in the range can result from more than one x in the domain. A function is one-to-one if each element in the range corresponds to exactly one element in the domain. So there is a restriction which makes a function a one-to-one function. In other words, function says x can't repeat. A one-to-one function says y cannot repeat either. A function f is one-to-one if for any two numbers a and b in its domain, f of a equals f of b results in a being equal to b. And when a is not equal to b, f of a is not equal to f of b. In other words, for a one-to-one, x of 1 is not equal to x of 2. That means f of x of 1 is not equal to f of x of 2. If it's not one-to-one, f of x of 1 equals f of x of 2, then x of 1 is not equal to f of x of 2. One way to understand the concept of inverse functions. F inverse of x is defined as the pair b comma a such that this line segment is read such that a and b would be an element of f of x. I've explained this in the previous recording. So simply interchange x and y, in this case, a and b. Domain of f equals range of f inverse, and range of f equals domain of f inverse. Domain and range interchange. For any one-to-one function f of x and its inverse f inverse, this is read f inverse. Their composite function f of f inverse of x equals x, f inverse of f of x equals x. In the first case, x in the domain of f inverse, the inner function. The second case, x is in the domain of f of x because f of x is the inner function when you do the composite function. To find the inverse function of a one-to-one function, number one, replace f of x with y. Number two, interchange the two variables x and y. Number three, solve the equation for y. And number four, finally replace y with f inverse of x, the inverse function notation. That is the process. 6.1 exponential functions. F of x equals a to the power of x. A must be positive and a can't be 1. It's a continuous function. And it's important to understand what I'm giving you here. There are various, reminding you of various exponential rules, such as the zero rule, exponential product rule, quotient rule, negative exponential rule, and so forth. So if we look at these three, here's the graph. The first one, y equals a to the power of x, and a is between 0 and 1. The last one, c, a is larger than 1. So this is exponential growth. This is exponential decay. If you choose base to be 1, you don't have an exponential function. What do you have? A horizontal line. So part B, this is not an exponential function, not an exponential function. HA, horizontal asymptote, in both cases, this one, so this graph as well as this graph represent exponential functions, not this one. This is just a horizontal line because the base is 1. Now, for these two cases, the horizontal asymptote is the x-axis, which has the formula y equals 0. They don't have a VA, vertical asymptotes. They don't have any. Both of them have the y-intercept located at 0, 1. X-intercept, they don't have x-intercept. Domain in both cases are real numbers from negative to positive infinity. Range from 0 to infinity, 0 is not included. In the case where a is positive, it's an increasing function, the exponential growth. As you can see, the limit of f of x as x approaches infinity is infinity, meaning the first quadrant, the end behavior. This is referring to the end behavior. As x goes to infinity, so does y. On the other hand, as x goes to negative infinity, we end up with 0. And this is actually the definition of a horizontal asymptote in calculus. When a is between 0 and 1, we have a decreasing function. We have an exponential decay. The limit of f of x as x approaches infinity is 0 in this case. But as it goes to negative infinity, y goes to positive infinity. So when f of x equals a to the power of x and a is larger than 1, it looks like this. This is one of those essential basic functions. And when a is between 0 and 1, it looks like this. So exponential growth, exponential decay. As the base gets larger, for example, comparing y equals 3 to the power of x and y equals 6 to the power of x, the function gets closer and closer to the y-axis. And on the other side, when a is between 0 and 1, the smaller the number, the closer to the y-axis. It rises faster. Now, f of x equals c a to the power of x, if we have a constant in front of that, where a is positive and a can't be 1, a is the growth factor. C is called the initial value, meaning if you set x equal to 0, you get c. F of x plus 1 divided by f of x. So if you replace this with x plus 1, becomes c a to the power of x plus 1. and f of x is c, a to the power of x, the ratio is a. Or f of x plus 1 is f of x times a. So please understand this means c a to the power of x plus 1 over c a to the power of x, which gives you a. Meaning, if delta y over delta x is constant, we know it's a linear function, rise over run. If ratio of consecutive outputs is a constant, it's an exponential. For example, f of x plus 1 over f of x is a constant, the same value. For example, f of x plus 2 over f of x plus 1 is also a. All right. Just to show you how the graph works, we've already discussed a general case, but when we start with a function, we just plot pairs. So let's plot those. For example, 0, 2 to the power of 0 is 1, 1, 2 to the power of 1 is 2, 2 squared is 4, 2 cubed is 8, 2 to the power of negative 1, that means 1 half, 2 to the power of negative 2, that means 1 over 2 squared or 1/4, 2 to the power of negative 3 is 1 over 2 cubed or 1 over 8. So if we plot those pairs, it looks like this. What about 3 to the power of x? We are going to do the same thing. We're going to use the same x coordinates, now the y coordinates. Obviously, 3 to the power of 0 is 1, 3 to the power of 1 is 3, 3 squared is 9, 3 cubed is 27. Negative 1, 3 to the power of negative 1 is 1/3, to the power of negative 2 is 1 over 9, 3 to the power of negative 3 is 1 over 27. And the graph looks like that. As you can see, they are similar, but if you graph them on the same set of axes, because the base is larger here, it gets closer to the y-axis. All of it, both of them, have the following. X-intercept, we don't have any. Y-intercept, in both cases, at 0, 1. Domain, all real numbers. Range, from 0 to infinity, but 0 is not included. Horizontal asymptote, the x-axis. What is the equation of x-axis? Y equals 0. Both cases are increasing functions. So this is an increasing function, so is this one. Graph the exponential function f of x equals 1/2 to the power of x. If we were to graph them by plotting points, for example, negative 4, 1/2 the power of negative 4 is 2 to the power of positive 4, which makes it 16. 1/2 the power of negative 3 makes it 2 cubed or 8. 1/2 the power of negative 2 makes it 2 squared or 4. 1/2 the power of negative 1 makes it 2. If I plug in, if I put 0, for example, I get 1. If I put 1, I get 1/2. If I put 2, I get 1/4, and so forth. So a bunch of pairs will do the job. And you can plot those pairs, and you're done. Obviously, that's an exponential decay because this number is between 0 and 1. Notice x-intercept, none, y-intercept 0, 1, domain, range, so far the same, horizontal asymptote. The difference is this, the decreasing function. Okay, class. The difference between this and the previous page, it's a decreasing function. Everything else is the same. Graph contains 0, 1. Also 1a and minus 1 and 1 over a. A is the base. If x is 1, you get a. Negative 1, you get 1 over a. That is always the case. The limit of f of x, as you have seen it in general, as x approaches negative infinity. So when we go this way, the y blows up to positive infinity. And this is notation, the limit notation. Lim stands for limit of f of x. As x approaching, that means it's getting closer and closer to negative infinity equals infinity. And the limit of f of x as x approaches infinity, as x goes towards infinity, the functional value, remember f of x represents the y coordinate, goes to 0. And that is the definition of horizontal asymptote. All right, we can do transformation. Let's go from y equals 2 to the power of x to 1/2 to the power of x, where 1/2 to the power of x is the same as 2 to the power of minus 1 to the power of x is the same as 2 to the power of minus x. Notice that. So you can replace the x with negative x, which means reflection about the y-axis. So first understand 1/2 to the power of x is the same as 2 to the power of minus x. So as we go from 2 to the power of x to 2 to the power of minus x, we're going to change the x to minus x. That means reflection with respect to the y-axis. That gives you the graph. So you can do it with transformation. Yeah, graph the exponential function by translation or transformation, where f of x is 2 to the power minus x minus 3. So we start with the basic y equals to the power of x. You can even start with 2 to the power minus x, which looks like that. But either way, there are different ways of approaching it. You can go to this one, or you can apply the negative 3, which means if you want to subtract 3, that means this shifts down by 3 units. This function shifts down by 3 units. All right, let's take it from the top again. We start with y equals 2 to the power of x. We could start with 2 to the power minus x, but either way, we are going to replace the x by minus x. In other words, reflection about the y-axis to get into 2 to the power of minus x. Or you could even start with this because we have seen that. And now we're going to subtract this, which means this function goes down by 3 units. So the effect is this 0, 1 goes down to 0, 1 minus 3, which makes it negative 2. This horizontal asymptote with the equation y equals 0 becomes the horizontal asymptote y equals 0 minus 3, which is y equals negative 3. Those are the effects. So therefore, it creates an x-intercept. The y-intercept, which was located at 0, 1 is 0 minus 2. The domain doesn't change our real numbers. The range changes, which was from 0 to infinity. Now it's from -3 to infinity. The horizontal asymptote y equals -3, it is still decreasing. So x-intercept, we're going to discuss it in a moment. Y-intercept is located at 0, -2. Domain is the same, all of them. Range, in these two cases from 0 to infinity, in this new case, from -3 to infinity. Horizontal asymptote in these two cases is the x-axis y equal to 0, but over here, y equals -3, and this is a decreasing function. Now, how do you find x-intercept? You set the function equal to 0, and you find it. This is solving this equation, and you have to use logarithmic properties. We'll discuss this type in a moment, but just to give you an idea, which is coming up, you say 2 to the power of minus x is 3, and then from here you have to take the log of both sides, common log, natural log, and solve it. So just in case if anybody is interested at this point, it's coming up. It's coming up. If I take the natural log of the left, natural log of the right, this becomes minus x ln 2. This becomes ln 3. And if you divide both sides by negative ln 2, so here, x is minus ln 3 over ln 2. That is the precise location. Needless to say, we put it into a calculator for an approximation. This is coming up later. Let's define the number e. We remember that from intermediate algebra, the base of a natural log. So here's the definition. If we have n, 1 over n, 1 plus 1 over n, and 1 plus 1 over n to the power of n, if we pick a bunch of numbers, 1, 2, 5, and make it huge, then we evaluate 1 over n. As you can see, this last one, for all practical purposes, 1 over n becomes almost nothing, 0. And then we're going to add 1 to that. So this becomes 2, this becomes 1.5, this becomes 1.2, all the way to the end. Now, if we raise this to the power of n, so what is n? 2 to the power of 1, that's 2. 1.5 to the power of 2, that's 2.25, so on and so forth. If you continue with that, this is an approximation for e. So e is defined as the limit of 1 plus 1 over n to the power of n as n approaches infinity. So let's look at this definition one more time. E is equal to limit of 1 plus 1 over n to the power of n as n approaches infinity. If you replace 1 over n with h, then n becomes 1 over h. As n goes to infinity, h goes to 0. This is an equivalent definition of that. Again, just to make sure we understand what happens here. If you let h be 1 over n, you get to this one. And that is an irrational number, 2.71828, and it continues indefinitely, just like pi. Also, E has the following definition. E is a number such that the limit of e to the power of h minus 1 over h as h approaches 0 equals 1. And we look at the proof of this one, for example, in calculus. So that's E. And the exponential function looks like almost any exponential function where a to the power of x, a is positive. So the same domain, all real numbers, the same range 0 to infinity, the same horizontal asymptote, which is the x-axis of y equal to 0, the same y-intercept, doesn't have an x-intercept, it's an increasing function. Graph the exponential function by translation. So y equals e to the power of x, we know it looks like similar to 2 to the power of x, 3 to the power of x. We go to minus e to the power of x, which is a reflection about the x-axis. So this one goes down like so. So y equals negative e to the power of x. Now to go to this, we're going to replace the x with x minus 3. That means move it to the right. So now move this one to the right by how many units? 3 units. So this is going to move to the right. Now bear in mind, when we flip it over, the horizontal asymptote doesn't change. The y-intercept of 0, 1 has changed to the y-intercept of 0, negative 1. Of course, it has changed the domain. The range, the domain is all real numbers, same here, but the range, which was 0 to infinity, is negative infinity to 0, just for the sake of argument. And here's the last one. We bring it down. And so it changes the location of the intercept, the horizontal asymptote remains the same, domain remains the same, and so forth. So here's how we are going to do the writing. X-intercept, none. We don't have an x-intercept. Y-intercept, we're going to discuss it in a moment. Domain remains the same. All of them are real numbers. Range has changed. Range for this one and this one are different. And this one and this one, both of them have from negative infinity to 0. The horizontal asymptote for all of them will remain the same, which is the x-axis, or y equal to 0. This is an increasing function. This is a decreasing function, and so is this one. This is a decreasing function. Now, so as we said, there is no x-intercept. But what about the y-intercept? Replace the x with 0. When I replace the x with 0 here, I get minus e to the power of 0 minus 3, which means negative e to the power of minus 3. So that would be the y-intercept. Replace the x with 0. Solve exponential equations. If a to the power of x equals a to the power of y, they have the same base, they must have the same exponent. X must be equal to 1. So this is one methodology if it's possible. Notice the left side has a base 2. The right side is 32, and we should know 32 is 2 to the power of 5. Now, they have the same base, namely 2, then they must have the same exponent. 3x minus 1 must be equal to 5. Move the 1 becomes 6, divide by 3x becomes 2. And you can check. You can always go back and check your work. E to the power of 2x minus 1 equals 1 over e to the power of 3x times e to the power minus x to the power of. So the left side has a base e. Let's see what we can do with the right side. This changes to e to the power of minus 4x, and it becomes the numerator. Now, e to the power of minus 4x over e to the power of 3x, you are going to subtract 3x from minus 4x. This is the exponential rule. Minus 4x minus 3x becomes minus 7x. I hope everybody remembers that. This is the quotient rule. That's what I'm using here. So this is minus 4x minus 3x. And so now 2x minus 1 must be equal to minus 7x. Nine x equals 1. X is 1 over 9. Three to the power of x plus 1 is 81. 81, we should know, is 3 to the power of 4. So x plus 1 must be 4 because they have the same base. They must have the same exponents. And x becomes 3 because you're going to subtract 1. Four to the power of 2x minus 1 is on the left. 8 to the power of x plus 3 is to the right. We don't see the same base. However, we should know 4 can be replaced with 2 squared. 8 can be replaced with 2 cubed. Now, the exponent for 2 on the left is 2 times 2x minus 1. The exponent for the 2 on the right is 3 times x plus 3, and those must be the same. So 2 times 2x minus 1 and 3 times x plus 3 must be identical. Four x minus 2 equals 3x plus 9. Move things around, x becomes 11. E to the power of minus x squared equals e to the power of x to the second power times 1 over e cubed. So first and foremost, we need to recognize the right side as e to the power of 2x over e cubed. So the right side is e to the power of 2x minus 3. They have the same base e, they must have the same exponent, so minus x squared must be equal to 2x minus 3. To solve this, we're going to move everything to the same side, and we're going to move it this way. We want a factor, so we want two numbers. The product is negative 3, the sum is positive 2, is positive 3 and negative 1. So x is either negative 3 or positive 1. 9 to the power of 2x times 27 to the power of x squared equals 3 to the power of -1. Well, on the right side, the base is 3. On the left side, we can change the 9 to 3 squared and 27 to 3 cubed. Therefore, this one becomes 3 to the power of 2 times 2x, which is 4x. This one becomes 3 to the power of 3 times x squared. And now the left side, we use the product rule, and we write it as 3 to the power of 4x plus 3x squared. So they have the same base 3, they must have the same exponent. Therefore, 4x plus 3x squared must be equal to -1. We move everything to the left because we want to do the factoring. It's a simple factoring because this is a prime number. So you have no choice but to go with 1 and 3. And this is just 1 and 1, either both positive or both negative. And because this is positive for both of them, positive. So this gives you x equals -1. This gives you x equals -1/3. We are done. Example 8, find the exponential function in the form of f of x equals c b to the power of x for this graph. So basically, what we are dealing with is that c is missing, b is missing, but we have two pairs. So we really use a system of equations to solve. So the two pairs are given. -1/3 is one of them, 1/4 is another one. So we use, for example, -1/3, -1, 3, which means replace the x with -1 and y, which is f of x, with 3. So 3 is cb to the power of -1. If we use this one, replace the x with 1 and f of x or y with 4/3. So these are the two equations in essence. Two equations, two unknowns. So if you go with the first one, cb to the power of -1 means c over b. So the relationship between these two is that if you do the cross product, c is 3 times b. So I hope everybody's fine with that. That's a simple cross product. C equals 3 times b. Over here, 4/3 is c times b to the power of 1 means cb. And we're going to replace the c with 3b. So 4/3 is cb. C is replaced with 3b, so this is 3b squared. Now, if I divide both sides by 3, divide this one by 3, divide this one by 3, you get 4/9 equals b squared. And b becomes plus minus 2/3. However, the base must be positive, right? The base must be positive for it to be an exponential function. So we go with only 2/3. So we know B is 2/3, and we know C is 3 times that. C is 3 times B, meaning 2. Now you go to this formula, f of x equals C, replace it with 2, times B to the power of x, 2/3 to the power of x. So into this formula, replace the B and C, f of x equals 2 times 2/3 to the power of x. Just for the sake of argument, if you replace the x with 1, you get 2/3 times 2, which is 4/3. If you replace it with -1, this becomes 3/2 times 2, which becomes 3. In other words, we just quickly checked it. Exponential probability, example 9. Between 9 p.m. and 10 p.m., cars arrive at Burger King's drive-thru at the rate of 12 cars per hour, or 0.2 car per minute. The following formula from the statistics can be used to determine the probability that the car will arrive within t minutes of 9 p.m. f of t equals 1 minus e to the power of -0.2t. Determine the probability that the car will arrive within 5 minutes of 9 p.m., that is before 9:05 p.m. Determine the probability that the car will arrive within 30 minutes of 9 p.m., that means before 9:30 p.m. So simply put, into this formula, replace the t with 5. You have to use a calculator. Minus 0.2 times 5 is -1. So e to the power -1 or 1 over e, 1 minus that gives us the following, and that's a percentage, about 63%. That's the probability of, that we are looking for. For part B, same formula. Now we replace the t with 30. So it's 1 minus e to the power -6. You put it into the calculator, gives you 0.9975, which is 99.75%. So simply put, plug in, everybody. Plug in. What value does f approach as t becomes unbounded in the positive direction? What this means is the following. What happens when t becomes huge? What happens when you take the limit of this function, f of t, this one, as t approaches infinity? This is t, everybody. That's the idea. So what happens as the time, the variable x or t, whatever it might be, it approaches infinity. That's the concept. Well, as t becomes larger and larger, just going back to parts A and B, notice this was e to the power of -1. Then t became larger, e to the power of -6. I hope you know that this is smaller than this. So as t becomes larger, this part becomes smaller and smaller. So as t becomes larger, this part becomes smaller and smaller. When t becomes huge, this goes to 0, because it's e to the power of ultimately negative infinity, which is 1 over e to the power of infinity. So this goes to 0. We get 1 minus 0 equals 1. We'll see this with more details in calculus, everybody. You don't have to worry about this too much, but understand the concept. Unbounded, in this case, the variable x or t or whatever the independent variable is, goes to infinity. Example 10, sketch the graph of the function y equals 3 minus 2 to the power of x and determine its domain and range. So we start with 2 to the power of x, which is very obvious. It's one of those elementary functions. We should be very comfortable. Now we go to negative 2 to the power of x, which means we are going to reflect the graph with respect to the x-axis. So if we change this to negative 2 to the power of x, that means reflection with respect to the x-axis. So flip this over. Now we apply the 3, that means bring it up 3 units. So shift the graph of y equals minus 2 to the power of x upward 3 units. So this one bring it up by 3 units, looking like this. So what is the domain? All of them the same, all real numbers from negative to positive infinity. But what about the range? I want to make sure everybody understand the range here is 0 to infinity. From here is negative infinity to 0, and here is negative infinity to 3. So minus infinity to 3. The effect is now we have a different horizontal asymptote, y equals 3. Pretty straightforward. This is your horizontal asymptote. Sketch the graph of the function y equals 1/2 e to the power minus x minus 1 and determine its domain and range. Again, let's start with the basic function y equals e to the power of x. Then we're going to go to e to the power minus x, which means you're going to change the x to minus x reflection about the y-axis. So reflect the graph of y equals e to the power of x, but the y-axis to get y equals e to the power minus x. So looking like that. Now we're going to use the 1/2. So it will shrink this function by a factor of 1/2. So compress the graph vertically by a factor of 2. So y becomes 1/2 of e to the power minus x. For the sake of argument, remember, the y-intercept was 0, 1 here, and it didn't change here. It's 0, 1. But now it goes down to 0, 1/2 as an example. So let me this one has coordinates 0, 1. And now minus 1. So this graph shifted down by 1 unit. So shift the graph down by 1 unit. And so what happens is that the horizontal asymptote becomes y equals -1, and this 0, 1/2 goes to 0, -1/2, looking like that. So this is the final translation. Again, this was 0, 1/2, now it's 0, -1/2. This was the x-axis of y equal to 0, it's y equals -1/2. So this point so what happens as far as the domain and range is concerned? Domain here, 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 all of them are real numbers. Domain hasn't changed. What about the range? The range 0 to infinity, 0 to infinity, 0 to infinity. But this one has changed because it has come down by 1 unit. So the range is from the horizontal asymptote from -1 to infinity. Of course, -1 is not included. Domain hasn't changed, all real numbers. You can write it in this format or in this format, interval format, negative to positive infinity means the same thing, but the range has changed. Solve the exponential equation, 5 to the power of x squared plus 8 equals 125 to the power of 2x. And we're going to use the same technique that we used before. Can we come up with the same base for both sides? This one has base 5. We can't change it. But this one, 125, we can change it to 5 cubed. When we change this to 5 cubed, 3 times 2x gives us 6x. Now these two must be identical because we have the same base. We must have the same exponents. We move everything to the same side for the sake of factoring. So x squared minus 6x plus 8. We want two numbers. The product is 8. The sum is -6. So -2, -4, which results in x being 2 and x being 4. So there are two answers, x equals 2, x equals 4.